Ever wonder how weather models predict the future? Scientists are constantly refining these tools to make forecasts more accurate, and here's a fascinating breakthrough. Let's break down how a new approach to training weather models is changing the game. The key lies in understanding weather's multi-scale nature. Imagine the atmosphere as a vast, interconnected system. Massive storm systems spanning continents, tiny gusts of wind, and everything in between. Traditional models treat all these scales equally, but what if we could teach machines to see the weather at different zoom levels? That's exactly what researchers at the European Center for Medium Range Weather Forecasts, ECMWF, are exploring with their model, AIFS-CRPS. So how does this work? AIFS-CRPS doesn't just predict the weather, it quantifies uncertainty. Think of it as a model that doesn't just say it'll rain tomorrow, but also tells you how confident it is and where surprises might occur. This is achieved through a scoring system called the Almost Fair Continuous Rank Probability Score, afCRPS, which acts like a referee grading predictions based on how well they align with real-world data. But here's the twist. Standard models struggle with weather's inherent multi-scale complexity. A hurricane's path might be predicted accurately, but the sudden thunderstorms it spawns, not so much. To fix this, researchers introduced a multi-scale loss function, a mathematical tool that teaches models to balance big-picture trends with small-scale chaos. Let's visualize this. Picture a sine wave representing weather data. A traditional model might treat the entire wave as one unit, but the multi-scale approach breaks it into parts. The long, slow undulations, like large weather systems, and the sharp, rapid fluctuations, like local turbulence. By training the model to evaluate each scale separately, it learns to balance accuracy across all levels of detail. In experiments, this approach outperformed traditional methods. When tested on simulated weather patterns, the multi-scale model correctly identified wave numbers, the frequencies of weather patterns that the old model missed. It's like giving the model a pair of glasses that let it see both the forest and the trees. What does this mean for real-world forecasts? Better predictions for extreme events. By respecting the atmosphere's multi-scale nature, models like AIFS-CRPS could help communities prepare for everything from regional floods to sudden heat waves. And the implications go beyond weather. This is a blueprint for training AI to handle any complex, multi-scale system, from climate modeling to financial markets. Let's dive into the science. Researchers tested two models using 38 years of weather data, 1979-2017, saving 2018 for testing. One used a scale-unaware loss function, like a camera with a fixed zoom. The other used a multi-scale loss, acting like a zoom lens that focuses on both big-picture patterns and fine details. Both models were tested in 2019, with forecasts starting from real-world data. The results? Both models had similar overall skill, but the multi-scale version shown in detail. Imagine a map of wind patterns. The scale-unaware model had more random, squiggly lines in areas with gentle changes, while the multi-scale model matched real-world data, Era 5, much closer, like a painter blending colors smoothly instead of splattering them. Think of it like editing a photo. A basic filter might make the whole image look good, but a professional tool lets you adjust shadows, highlights, and textures separately. The multi-scale model does something similar for weather, fine-tuning details without overcomplicating the big picture. By analyzing spectra, which measure weather patterns at different scales, the team found the multi-scale model better controlled tiny fluctuations. This matters because too much noise in forecasts can lead to errors, predicting a storm where none exists or missing a subtle shift in wind direction. While the multi-scale approach adds a tiny bit of computational work, the payoff is clearer, more realistic forecasts. This could help meteorologists warn communities about extreme weather more accurately. And as models get smarter, we might see even better predictions for everything from daily commutes to climate change impacts. So next time you check the weather app, remember, behind those predictions is a world of math, physics, and a little bit of scale-aware magic. Thanks for watching, stay curious and keep an eye on the skies. Imagine trying to predict the weather a week from now. It's tricky, right? The atmosphere is chaotic, like a giant, ever-changing puzzle. But scientists are using cutting-edge tools to make these predictions smarter, and here's where it gets fascinating. A few years back, researchers discovered something counterintuitive. More accuracy can come from less precision. Think of it like this. Instead of crunching every tiny detail with super high resolution, models can focus on the big picture. This idea from a 2021 study showed that simplifying data inputs while refining how models process them could actually improve forecasts. It's like learning to ride a bike by focusing on balance, not every tiny wobble. But how do you handle all that uncertainty? Enter ensemble forecasting, a method where scientists run multiple simulations with slightly different starting conditions. It's like asking a group of experts to guess the weather. Their varied answers give a range of possibilities. A 1996 paper on the ECMWF system, Europe's weather forecast powerhouse, laid the groundwork for this, showing how blending many predictions reduces errors. Now fast forward to today. Machine learning is shaking things up. Take Diffusion-LAM, a 2025 model that uses diffusion techniques. Think of it as a digital weather artist adding and removing noise to generate forecasts. Or GenCast, a 2023 AI that uses similar methods to predict weather patterns. These models don't just guess. They learn from decades of data, like a student studying past exams to ace the next one. Here's the twist. Some researchers are betting on probabilistic models that don't just say it'll rain, but quantify how likely that is. A 2024 study used generative networks to turn weather predictions into probabilities, giving us not just a forecast, but a map of possibilities. It's like getting a 70% chance of sunshine, instead of a yes-no answer. But what about the math behind it all? Techniques like score-based generative models and Bayesian inference are reshaping how we evaluate predictions. These methods allow models to not only predict outcomes, but also express confidence intervals, making forecasts more actionable for decision makers. As we push the boundaries of AI and weather science, the future looks brighter, literally. From hyperlocal forecasts to climate resilience planning, the next generation of models is poised to transform how we interact with the planet's most unpredictable system. Stay curious, and let's keep exploring the world of data and discovery together.